Hi folks, today we're going to talk about piecewise functions and the difference quotient. We'll jump right into it with piecewise functions. You've seen these before probably last year in Algebra 2, but by definition it's just a function that is defined by two or more equations over a specified domain. So here are a couple of examples of some piecewise functions. You'll notice in the graph on the left that is a piecewise function made up of all linear functions. The graph on the right is a piecewise function made up of a constant function and a quadratic function. Okay, so a couple different types. You'll notice in both of these that the domain of both of these, right, is all real numbers. And remember, we can write it in this form, or if we write it in interval notation, that would be from negative infinity to positive infinity. And the same thing here, even though there's an open circle there, we pick up the function down here with that closed circle. And again, our domain would be all real numbers or from negative infinity to positive infinity. So you can have different types of functions combined within that piecewise function. Or you don't have to have a function, a piecewise function that covers all real numbers in its domain. So if you look at this one, you can see here that the domain on the left-hand side, because there's an arrow, that goes all the way to negative infinity. And you'll see here, we pick up all these points here. We don't have any breaks in our domain, but we do have a stoppage in our domain when we get to here. And so our domain actually only goes up to and including 6. Okay, so lots of different ways we can represent and look at a piecewise function. We can also graph a piecewise function. Let's say, for example, our function is f of x is equal to 3 if x is less than or equal to negative 1, x minus 2 if x is greater than negative 1. So we have this constant component, or that constant function, when x is less than or equal to negative 1, and a linear function when it's greater than 1. And so if we were to go ahead and graph that, it's pretty straightforward, right? When x is less than or equal to negative 1, my function is going to be equal to 3, which means I would have a closed circle there. I have this constant function, and so I just have this horizontal line going all the way in that direction. Okay. The other component of that is x minus 2 when x is greater than 1. Looking at that, it's pretty straightforward to graph it. Our y-intercept is at negative 2. Our slope is 1, which we can tell from the graph there, and we can go ahead and graph that. And remember that we have to carry this all the way down to where x is negative 1, but because it's, where x is greater than 1, but because this is just a greater than symbol, we have to have an open circle there. If we had a closed circle, then this wouldn't even be a function because it wouldn't pass that vertical line test. Okay, so you're just going to, when you're graphing, you're just going to graph those pieces of the function, hence that piecewise function. Another one that comes up is a step function, or the greatest integer function. You'll see it written a couple different ways. Sometimes you'll see it written like this, or you might see it written like this. And they mean the same thing. The greatest integer function is the largest or the greatest integer less than the number. So if you think of just the number 2, right, the largest integer or the greatest integer less than or equal to 2 is 2. Right? That's the greatest integer less than or equal to 2. But then when you start getting into decimals, let's say 2.5, the greatest integer less than or equal to 2.5 is also going to be 2. And so you can take all of the decimal values between 2 and 3, right? I can go up to 2.9, and the greatest integer less than or equal to 2.9 is also 2. So you can almost think of it, and this is how I remember it, I call it the look to the left function, because you're looking to the left on the number line. So what integer is to the left of 2.9? It would just be 2. So if you were graphing that, right, at 2, my function is equal to 2. At 2.5, my function is equal to 2. At 2.9, my function is equal to 2. So all in here, my function is equal to 2. But then what happens when I get to 3? Well, the greatest integer less than or equal to 3 is 3. So now I step up to 3. And if I'm going to have a closed circle there, I have to have an open circle there. And then the same thing happens as you go through the different x values between 3 and 4. And then you step up to 4. And that is how the graph is generated. And you can go ahead and fill in all of those values. And it works the same with the negative numbers, because you could just follow this function all the way across your graph. Okay? So I'm just going to fill in those, but it does work the same with the negative numbers, right? The greatest integer less than or equal to negative 1.5, the greatest integer less than or equal to negative 1.5 is negative 2, right? The greatest integer less than it. So you'd have to go down to negative 2. So you'll see here the steps work the same way. Okay, the steps work the same way. And you could go ahead and fill all of those in. Okay, so that is your step function. Let's then talk about the difference quotient. And this is going to come up a lot a couple sections from now when we start talking about rate of change and average rate of change in a function. But it does come up here in the book, so I do want to go over it with you. The difference quotient is simply this. It's f of x plus h minus f of x over h. And I'm going to show you how to find it. And once we get to that whole idea of rates of change, I'll explain more of what it is and what's going on. But for now, let's just go through the motions of how to actually find the difference quotient. So let's say I have the function f of x is equal to negative 2x squared plus x plus 5. Okay, so I am simply going to determine what my difference quotient is. So the first thing I have to do is find f of x plus h. And all that means is everywhere in my function where I see x, I'm replacing it with x plus h. So I am just going to go ahead, x plus h plus 5. Then I have minus f of x, so I'm going to plug that in, negative 2x squared plus x plus 5. All of that is over h. So now I'm just going to go through and do that out. So I have negative 2. If I expand my binomial, right, I have x squared plus 2xh plus h squared plus x plus h plus 5 plus 2x squared. Now I'm going to distribute this negative, minus x minus 5. I have all of that over h. Okay? And now if I go ahead and distribute my negative 2, I have negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5 plus 2x squared minus x minus 5. All of that over h. And so now what I'm going to do is I'm going to combine my like terms. So I have negative 2x squared and positive 2x squared. Those are going to cancel. I have positive x and negative x. Those will cancel. I have positive 5 and negative 5, and those will cancel. So I'm going to finish my problem up here. So with all of those terms canceling, I'm left with let's see, negative, if I write this out, I have negative 4xh minus 2h squared plus h. Don't forget that plus h that's in there. All of that over h. And now I can go ahead and I can factor out an h because I do want to simplify this. So I have h times negative 4x minus 2h plus 1 over h. Those h's are going to cancel, and so I'm left with negative 4x minus 2h plus 1. And that is my difference quotient for that problem. So it's really easy to make careless mistakes when you're doing these problems. It's easy to lose a term in there or mix up a sign, and then that messes things up. So be really careful when you're doing these. But that's the general gist of the difference quotient. Like I said, we'll talk about it in more detail in upcoming sections. And that's it for today. Hopefully that'll help you out with the assignment. Have a great rest of your day, and I will see you next time. Take care, everybody.